Hello and welcome back. In today's video, I'm overclocking the Intel Core i9-14900K processor all the way up to 6.2 GHz using the GIGABYTE Z790 Aorus Master X motherboard and EK Quantum custom loop water cooling. This is the very first overclocking guide I'm making for Intel's 14th gen Core Raptor Lake Refresh processor, and it took me quite some time to complete it. That's both because I traveled to Europe during the time that I was supposed to complete the guide, and also because I ran into a couple of interesting issues, which I hope I can detail and explain to you in this video. All right, let's jump straight in. The Intel Core i9-14900K is the flagship processor of Intel's 14th generation core processor lineup, codenamed Raptor Lake Refresh. The Raptor Lake Refresh processors launched on October 17, 2023, about 1 year after the launch of the original Raptor Lake processors. It should come to no surprise if I say that Raptor Lake Refresh processors are identical to Raptor Lake processors in pretty much every aspect, bar specifics such as frequency, core count, and L3 cache of specific SKUs. Intel Raptor Lake Refresh builds on the same performance hybrid architecture introduced with the 12th generation Alder Lake, so it also features performance P-cores and efficient E-cores. Like the 13th gen Raptor Lake, it is built using an improved process dubbed Intel 7 Ultra. Compared to its Core i9-13900K predecessor, launched 1 year ago, the 14900K has a 200 MHz higher base and maximum boost frequency. The exact specification of the Core i9-14900K is a bit unclear. As you may have noticed, some media say the maximum all-core boost is 5.7 GHz, but Intel's product page says the maximum turbo boost 2.0 frequency is 5.6 GHz. Things are a bit confusing because the CPU supports TVB and ABT technologies, and it's a bit unclear how much frequency each of these technologies add to the CPU. After a bit of research, I assume the official specification of the 14900K is as follows. The P-core base frequency is 3.2 GHz. The Turbo Boost 2.0 frequency is 5.6 GHz, meaning every P-core can boost to 5.6 GHz. Traditionally, this frequency is only available for up to 2 active P-cores. As more cores activate, the maximum frequency would then drop gradually, but that's unclear for the 14900K. The Turbo Boost Max 3.0 frequency is 5.8 GHz for up to 2 active P-cores. However, only the favored cores can boost to 5.8 GHz. The others are limited to 5.6 GHz. When thermal velocity boost is active, the 2 favored P-cores can boost to 6 GHz. Typically, TVB also adds an extra ratio in scenarios where more than 2 cores are active, but again, that's unclear for the 14900K. In addition, the TVB temperature has traditionally been 70 degrees Celsius. However, that's also unclear for the 14900K, as 6 GHz can be reached even when the cores are 100 degrees Celsius. The specification is unclear because of the adaptive boost technology. This technology was first introduced with the 11900K, and it provides a significant performance boost, overriding many of the other turbo boost technologies. In the case of the 14900K, when ABT is enabled, up to 8 P-cores can boost to 5.7 GHz even when all P-cores are active. But it's important to remember that ABT is fused enabled and cannot be disabled by the end user. So what you'll see in the operating system is that the CPU will boost to 6 GHz when 2 favored cores are active, and up to 5.7 GHz when any non-favored core is active, up to when all the P-cores are active. The E-core base frequency is 2.4 GHz, and the E-core maximum boost frequency is 4.4 GHz for all cores and all boost scenarios. In this video, I'm covering 4 different overclocking strategies. First, we unleash the Turbo Boost 2.0 limits and enable XMP 3.0. Second, we overclock using Foundation Toolkit and Intel Speed Optimizer. Third, we get into simple manual overclocking. And lastly, we dive a little bit deeper into the overclocking toolkit for an advanced overclock. However, before we jump into the overclocking, let's first have a look at the benchmarks and the hardware that we'll be using in this guide. The system we're overclocking today consists of the following hardware. The Easy Fan Controller SkatterBencher Edition, or EFC-SB, is a customized version of the EFC fan controller that I've used many times on this channel already. By connecting the EFC-SB to the EVC2 device, I can monitor the ambient temperature, water temperature, and fan duty cycle. I also use the Elmo Labs EFC-SB to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC-SB. Then I use the low-high setting to map the fan curve from 25 to 40 degrees water temperature. I use this configuration for all my overclocking strategies. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. It is the very first time that I'm using the OCCT application in my overclocking guides instead of Prime 95. Now, I want to take a couple of minutes to explain why that is. The main reason to consider swapping out Prime 95 for OCCT came after a couple of weeks of struggling to determine why the effective core clock readings kept dropping during a Prime 95 workload, especially with higher speed memory. For those who are unaware, we must differentiate between the set or target clock and the effective clock on modern chips. The target core clock is set by the base clock frequency and a multiplier. In contrast, the effective core clock is the actual number of clock cycles across a given period. The effective clock is an essential metric because that's what drives compute performance. Since I want to measure the improvement in core frequency during a worst-case stress test, I want to check the average effective clock of the P cores and the E cores. The OCCT CPU stability test with a small dataset in extreme mode and steady load type gave me the highest load in terms of power consumption and a stable effective clock. As I got to explore the OCCT software during my testing period, I became intrigued by the many options available for stress testing, and it seems like the community is also pretty positive about this software. So I'll be looking to integrate it more in future SkatterBencher guides. Before we jump into the overclocking, of course, we have to check the performance at default settings. Please note that this Z790 Aorus Master X motherboard comes with a pretty non-standard default configuration, including adjusted power limits and an AVX negative ratio offset of -7. So in order to get the stock performance of this 14900K, we first have to go into the BIOS and switch to advanced mode. In the tweaker menu, enter the advanced CPU settings submenu, set AVX settings to user defined, set AVX optimum to enabled. Set turbo power limits to Intel POR. Then save and exit the BIOS. The default Turbo Boost 2.0 parameters for the Core i9-14900K are as follows. We use the extreme specification for measuring stock performance. Here's the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 4858 MHz, and the average CPU E-core effective clock is 3874 MHz with 1.053 volts. The average CPU temperature is 75 degrees Celsius. The ambient and water temperatures are 26.6 and 29.8 degrees Celsius. The average CPU package power and CPU input power are 253 and 258.4 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5049 MHz and the average CPU E-core effective clock is 3958 MHz with 1.105 volts. The average CPU temperature is 74 degrees Celsius. The ambient and water temperatures are 26.2 and 29.4 degrees Celsius. The average CPU package power and CPU input power are 253 and 256.9 watts. Now let us try our first overclocking strategy, but before that, make sure to locate the Clear CMOS button. Pressing the Clear CMOS button will reset all your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. However, it does not delete any of the BIOS profiles previously saved. In our first overclocking strategy, we take advantage of unleashing the Turbo Boost 2.0 power limits and enabling Intel Extreme Memory Profile. Turbo Boost 2.0 is a performance-enhancing technology that allows the processor to run faster than the base specification if it's operating within or below rated power, current, and temperature limits. The ultimate advantage is, of course, that you get extra performance in primarily multi-threaded applications, but sometimes also single-threaded applications. The Turbo Boost algorithm works according to a proprietary EWMA formula. This stands for exponentially weighted moving average. There are 3 parameters to consider: PL1, PL2, and tau. Obviously, Turbo Boost 2.0 is available on Raptor Lake Refresh processors, as it's the primary way to get more performance over the base specification. An easy unleash option in the GIGABYTE perf drive allows you to unlock the Turbo Boost power limits. Adjusting the power limits is, strictly speaking, not considered overclocking, and that's because we don't change any of the thermal, electrical, and frequency parameters. Intel provides the Turbo Boost parameters as guidelines to motherboard makers and system integrators to ensure that their CPU can run the base configuration on those motherboards and in those systems. But as we all know, better motherboard designs or better thermal solutions or better system configurations can enable peak performance for much longer. Intel Extreme Memory Profile, or XMP, is an Intel technology that lets you automatically overclock your system memory. Essentially, it is an extension of the standard JEDEC specification and allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. Intel Extreme Memory Profile 3.0 is the new XMP standard for DDR5 memory. It is primarily based on the XMP 2.0 standard for DDR4, but has additional functionality. There's a lot more to the new XMP 3.0 standard, which falls outside of the scope of this overclocking guide. Check out my Alder Lake launch video if you want to learn more about XMP 3.0. Upon entering the BIOS, switch to Advanced mode. In the Tweaker menu, set GIGABYTE perf drive to unleash. Enter the Advanced CPU settings submenu. Set AVX settings to user-defined. Set AVX optimum to enabled. Leave the Advanced CPU settings submenu. Set Extreme Memory Profile XMP to XMP1. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. As expected, since we're not increasing the frequency of the CPU cores, the performance improvement is relatively limited. That said, improving the memory performance by using XMP 3.0 and providing more headroom for power consumption helps improve performance in specific workloads. We see the highest performance improvement of plus 15.70% in AI benchmark. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5309 MHz and the average CPU E-core effective clock is 4234 MHz with 1.188 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperatures are 28.2 and 32.3 degrees Celsius. The average CPU package power and CPU input power are 376.9 and 398.7 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5478 MHz and the average CPU E-core effective clock is 4221 MHz with 1.234 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperatures are 27.4 and 31.7 degrees Celsius. The average CPU package power and CPU input power are 372 and 390.2 watts. In our second overclocking strategy, we leverage the Intel Speed Optimizer functionality available in the Foundation Toolkit software. I talked a little bit already about the Foundation Toolkit in a separate video on this channel, but the long story short is that it's a CPU silicon customization software developed by Matthias from Benchmade and myself. While we have big dreams for the application in the long term, at the moment it only integrates the Intel Extreme Tuning utility. The Foundation Toolkit enables precise CPU performance tuning and caters to Intel KSQ CPU users. Currently, the application is publicly available for anyone to try. However, please be aware that the Foundation software presently offers limited functionality. One of those functionalities is the Intel Speed Optimizer we're using in this OC strategy. Intel Speed Optimizer, or ISO, is a performance-enhancing technology embedded in the Intel Extreme Tuning Utility software. Its primary purpose is to simplify overclocking. If your processor supports ISO, you can enable higher performance by clicking a single button. ISO should stay enabled even after rebooting the system. After enabling ISO, the following settings have changed. As you can see, ISO primarily relies on enabling higher power limits and slightly boosting the CPU core frequency to improve performance. The OCTVB configuration ensures default CPU performance above 90 degrees Celsius. First, go into the BIOS and, in easy mode, set Extreme Memory Profile XMP to XMP1. Then save and exit the BIOS and reboot the system. Upon entering the operating system, go to the Foundation Toolkit website, make sure to install the software, browse to the ISO tab, click Enable Optimizer. We rerun the benchmarks and check the performance increase compared to the default operation. The extra bump in frequency helps add a little bit more performance in both light, single-threaded workloads and heavy all-core workloads. We see the highest performance improvement of plus 19.72% in AI benchmark. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5282 MHz and the average CPU E-core effective clock is 4226 MHz with 1.187 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperatures are 28.6 and 32.6 degrees Celsius. The average CPU package power and CPU input power are 373.8 and 395.8 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5446 MHz and the average CPU E-core effective clock is 4292 MHz with 1.227 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperatures are 27.9 and 32.1 degrees Celsius. The average CPU package power and CPU input power are 368.3 and 386.4 watts. In our third overclocking strategy, we pursue a simple manual overclock that's centered around two key activities. Try to increase the CPU frequency where possible and try to undervolt the CPU where possible. Do note that I won't dig too much into the details of the voltage configuration, as that is part of our next overclocking strategy. So I'll rely mostly on the motherboard auto rules for any of that kind of configuration. Generally speaking, there are two ways that you can configure the CPU ratio on Intel processors: sync all core or set a turbo ratio configuration. Sync all cores sets a single fixed ratio applied to all cores. This is very much the historical way of Intel CPU overclocking. Turbo ratio configuration allows us to modify the default Intel frequency specification and configure an overclock for various scenarios. Before we go any further, there are three critical elements to understand about a turbo ratio configuration. First, you can configure the maximum allowed CPU core ratio for any number of active cores. Second, you can configure the maximum allowed CPU core ratio for a given CPU core. And third, the turbo ratio configuration for P-core and E-cores is independent. To explain the first point, let's have a look at the default configuration of the 14900K. The 14900K has a total of 8 P-cores. Therefore, we can configure the maximum allowed P-core ratio for when 1 P-core is active, when 2 P-cores are active, all the way up to when 8 P-cores are active. The standard configuration allows every P-core to boost to 5.7 GHz when all cores are active. In our overclock, we adjust the turbo ratio configuration to boost to 6.1 GHz when up to 6 P-cores are active and up to 5.7 GHz when up to 8 P-cores are active. To explain the second point, let's consider the 14900K default specification again. While the 14900K has 8 identical P-cores, 2 of those cores are called the favored cores. The maximum allowed frequency for the favored cores is 6 GHz, whereas the others are limited to 5.7 GHz. Often, we use the per core ratio limit to prevent the weaker cores from boosting to the higher frequencies. In this strategy, we let all cores boost to the maximum 6.1 GHz, so I'll cover the per core ratio limit function in the next overclocking strategy. To explain the third point, again, let's refer to the 14900K specification. The CPU has a total of 8 P cores and 16 E cores. While the P cores can boost up to 6 GHz, the E cores can only boost up to 4.4 GHz. The P core rules for the maximum allowed frequency can also be applied to the E cores, however, with one major caveat. The E core CPU ratio can only be controlled in groups of 4 E cores. So for the 14900K, since it has 16 E cores in total, we can configure the maximum allowed core ratio for 4 groups of 4 E cores. However, we can still configure the maximum allowed frequency for one active E core up to 16 active E cores. In this OC strategy, we are not touching the E core frequency. As we've seen in the previous overclocking strategy, once we open up the power limits on this 14900K, it very quickly shoots up to the TJ max of 100 degrees Celsius. So, as many enthusiasts know very well, undervolting is a key method of increasing the performance of this 14900K processor. There are many ways to undervolt your Core i9-14900K. I will discuss this at length in the next OC strategy. For this OC strategy, we're relying on the Intel Advanced Voltage Offset tool. Advanced Voltage Offset, better known as the VF points, is an extension of the adaptive voltage as it exposes some of the points of the factory fused voltage frequency curve to the end user and allows for manual adjustment of these points. Overclockers commonly use the Advanced Voltage Offset or VF points in two ways. First, you can configure a positive voltage offset for the highest VF point, which helps achieve a higher single-threaded boost frequency. Second, you can configure a negative voltage offset for the lower VF points. That helps achieve lower voltage for all-core boost, which results in a lower temperature in all-core boost, and thus potentially higher overclocking headroom. On Raptor Lake Refresh processors, the CPU P cores have 15 distinct voltage frequency points. However, only points 1 to 11 are in use. Furthermore, some points can be copies of other points. To undervolt the CPU in all core workloads, we have to adjust VF points 6, 7, and 8, as these control the voltage floor ratios between 51x and 57x, where we end up in an all-core AVX2 and SSC workload. The VF point configuration is, for most users, including myself, mostly trial and error. However, there is a systematic element to it. Let's say you want to lower the CPU voltage at 5.4 GHz, so when we use ratio 54x. We know that the voltage for 54x is interpolated between the VF points 6 and 7. So we can lower the voltage for 54x by reducing VF point 6, which also affects the voltage for ratios between 43x and 51x, or by lowering VF point 7, which also affects the voltage for ratios between 56x and 58x. I set a negative voltage offset for VF points 5, 6, 7, and 8 in this OC strategy. Thus, we undervolt the CPU for frequencies between 3.4 GHz and 6 GHz. Whenever you venture into the manual overclocking of an Intel CPU, I always recommend to disable the thermal velocity boost voltage optimizations, especially if you want to also manually tune the voltages. Thermal velocity boost is an Intel technology that exploits the fact that CPUs need less voltage to run a specific frequency when the operating temperature is lower. The CPU automatically adjusts the voltage according to the operating temperature when this setting is enabled. Here you can see an example with the Core i9-13900K processor when thermal velocity boost voltage optimizations are enabled. The difference in operating voltage at 40 degrees Celsius and 100 degrees Celsius is about 50 millivolt. Suppose you don't disable these voltage optimizations. In that case, you might run into a situation where your CPU is stable at 100 degrees Celsius during a heavy load, but crashes due to too much undervoltage when the CPU is 40 degrees at idle in desktop. A last setting, or two settings, I want to discuss before moving on to the BIOS configuration is the high bandwidth and low latency options in the GIGABYTE BIOS. I used these settings before in previous guides, and they do seem to provide additional performance benefits. Unfortunately, GIGABYTE is pretty tight-lipped on what it does exactly. Enabling the settings may cause instability, so it's up to you to see if your memory is stable when you enable these. Upon entering the BIOS, switch to Advanced Mode. In the Tweaker menu, set GIGABYTE Perf Drive to Unleash. Enter the Advanced CPU Settings submenu. Set Voltage Reduction Initiated TVB to Disabled. Set AVX Settings to User Defined. Set AVX Optimum to Enabled. Set Active Turbo Ratios to Manual. Set Turbo Ratio 1 P-Core Active to 6 P-Core Active to 61. Set Turbo Ratio 7 P-Core Active and 8 P-Core Active to 57. Set Turbo Per Core Limit Control to Manual. Set Turbo P-Core 0 to 7 Ratio Limit to 61. Leave the Advanced CPU Settings submenu. Set High Bandwidth to Enabled. Set Low Latency to Enabled. Set Extreme Memory Profile XMP to XMP1. Set vCore Voltage Mode to Adaptive vCore. Set VF Offset Mode to Selection. Set VF.5 offset to -15 mV. Set VF.6 and 7 offset to -50 mV. Set VF.8 offset to -35 mV. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. We're not pushing the operating frequency much higher than the base specification. Still, thanks to the undervolting, there's some improvements in all-core and heavy workloads. We get a maximum performance improvement of plus 22.71% in AI benchmark. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5344 MHz, and the average CPU E-core effective clock is 4283 MHz with 1.183 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperatures are 28.6 and 32.7 degrees Celsius. The average CPU package power and CPU input power are 373.8 and 395.5 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5582 MHz, and the average CPU E-core effective clock is 4211 MHz with 1.22 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperatures are 28 and 32.2 degrees Celsius. The average CPU package power and CPU input power are 365.7 and 383.6 watts. In the fourth and final overclocking strategy of this guide, I'm pursuing an advanced manual overclock. The main focus of this advanced manual overclock is the voltage configuration. So during this overclocking strategy, I'll try to explain to you all of the different settings that I'm using to create a more neater voltage configuration. And then afterwards, let's see if we can also get a little bit of extra frequency. So to kick things off, let's first have a look at the Raptor Lake Refresh voltage topology. On Raptor Lake Refresh, the VCCIA voltage rail drives the voltage for the CPU cores, P-core and E-core, and the ring. That means a single voltage is used for all these parts of the CPU. How that voltage is configured is straightforward yet complex. 6 main elements impact the voltage of this VCCIA voltage rail. We can split these elements into 2 groups. Those that affect the voltage requested by the CPU to the motherboard voltage regulator, and those that impact the voltage delivery from the motherboard voltage regulator to the CPU die. In the coming minutes, I will explain how each of these settings can impact the voltage of your CPU. As a first step, let's have a look at all the different technologies that can affect what voltage the CPU requests from the motherboard voltage regulator. An Intel CPU relies on a lot of factory-fused voltage frequency curves to manage the dynamic compute performance of the chips. A factory-fused voltage frequency curve essentially defines the relationship between an operating frequency and the voltage that's required to run that frequency. A lot of different parts inside your CPU have such a factory-fused voltage frequency curve, including the ones that affect the VCCIA voltage rail. In the case of the Core i9-14900K, the VCCIA voltage rail is affected by no less than 13 different voltage frequency curves. Based on these VF curves, to get a specific voltage provided by the VCCIA voltage rail, the CPU issues an SVID request to the voltage controller. The VID requested is the highest among all the requested voltages according to every VF curve affecting the voltage rail. Intel offers users a number of methods to adjust that SVID request from the CPU to the motherboard voltage controller. To keep things simple, let's have a closer look at how we can do that for the CPU P cores. The two main methods to adjust the CPU core voltage are override and adaptive mode. Override mode specifies a single static voltage across all ratios. It is mainly used for extreme overclocking where stability at high frequencies is the only consideration. Adaptive mode is the standard mode of operation, which relies on the factory-fused voltage frequency curves we discussed before. We can configure the voltage in override and adaptive mode directly in the CPU PMU or Power Management Unit. We can specify a target voltage and a voltage offset for each mode. When we set an adaptive target voltage for a core, this voltage is mapped against the OC ratio. The OC ratio is the highest ratio configured for the CPU across all settings and cores. When you leave everything at default, the maximum default turbo ratio determines the OC ratio. In the case of the 14900K, that ratio would be 60x. The OC ratio equals the highest configured ratio if you overclock. There are several rules that govern adaptive voltage mode. The voltage set for a given ratio n must be higher than or equal to the voltage set for ratio n-1. Suppose our 14900K runs 60x at 1.43 volt. Setting the adaptive target voltage mapped to 60x lower than 1.43 volt is pointless in that case. 60x always runs at 1.43 volt or higher. Biases may allow you to configure lower values, however, the CPU's internal mechanisms will override that configuration if it doesn't follow the rules. The adaptive target voltage configured for any ratio below the maximum default ratio is ignored. Take the example of the 14900K specified to run 60x at 1.43 volt. Suppose you try to configure all cores to 55x and set 1.25 volt. In that case, the CPU ignores this because it has its own factory-fused target voltage for all ratios up to 60x and it uses that voltage. You can only change the voltage of the OC ratio, which, as I mentioned before, on the 14900K is 60x and higher. For ratios between the OC ratio and the next highest factory-fused VF point, the voltage is interpolated between the set adaptive voltage and the factory-fused voltage. Returning to our example of the 14900K specified to run 60x at 1.43 volt, let's say we manually configure the OC ratio to be 65x at 1.5 volt. The target voltage for ratios 61x, 62x, 63x, and 64x is now interpolated between 1.43 volt and 1.5 volt. Modern CPUs like the 14900K have many more tools that allow us to tune the factory-fused voltage frequency curves. The critical thing to remember about all of these options is that ultimately these options determine the SVID request from the CPU to the motherboard voltage regulator, which in turn sets the voltage for the VCCIA voltage rail. Specific types of workloads can also affect the SVID request from the CPU to the motherboard voltage regulator. A prime example of that is the AVX guard band and the associated AVX guard band scale factor. The guard band effectively serves as an upper and lower limit to the voltage request. Since Rocket Lake, end users can make minor adjustments to the AVX guard band by using the AVX guard band scale factor. Unfortunately, I can't really add that much commentary on this tool's effectiveness as I haven't dug too deep into this tool. Note that I'm not talking about the AVX ratio offset tool, which reduces the CPU ratio when AVX instructions are used. We'll talk about those later in the video. As I discussed earlier in the video, thermal velocity boost is an Intel technology that exploits the fact that the CPU needs less voltage to run a specific frequency when the operating temperature is lower. When we have this setting enabled, the CPU automatically adjusts the voltage according to the operating temperature by adjusting the CPU SVID request to the voltage controller. A critical aspect of this SVID voltage request is that there's an assumption that whatever voltage the CPU requests to the motherboard voltage regulator is also the voltage that will end up at the CPU die. But that's not always the case because there are a lot of electrical components between the motherboard voltage regulator and the CPU die. Two main elements will affect the voltage delivered to the CPU die: the AC load line and the motherboard voltage regulator configuration. The AC load line is a tool made available to motherboard engineers to bring into the voltage equation also the motherboard's electrical impedance. Electrical impedance is the opposition to alternating current and can be affected by the motherboard design, the PCB quality, and the choice of the electrical components. Electrical impedance can significantly affect the effective voltage at the CPU die. Adjusting the AC load line offsets the requested voltage to account for any electrical impedance. A higher AC load line setting will yield a higher effective voltage. For example, suppose we know that a 1.4 volt voltage output by the controller, as requested by the CPU, results in an effective voltage of 1.35 volt at the CPU die due to electrical impedance. In that case, we can configure the AC load line such that the CPU requests 1.45 volt instead, making up for the difference. An option tightly related to the AC load line is the DC load line. We must first discuss the motherboard voltage regulator configuration to understand its purpose. The motherboard voltage regulator, or MBVR, is a critical part of a motherboard design. Essentially, without an MBVR, there's no CPU voltage. Nowadays, these motherboard voltage regulators are pretty complex microcontrollers with a wide range of configuration options. But for the purpose of this guide, we can limit ourselves to two options: voltage override and the load line. I can be short about the voltage override. Most voltage regulators allow you to override the requested voltage with a static voltage or offset. The VR load line is essential for the V-droop and voltage under an overshoot. V-droop is the decrease in voltage when the CPU goes from idle to load based on the electrical current. You want your CPU to be stable in all scenarios, so knowing the lowest voltage the CPU runs at is very important. After all, if the voltage is too low, the overclock won't be stable. Undershoot and its counterpart overshoot are brief voltage spikes when the CPU switches from idle to load or from load to idle. These spikes cannot be measured easily and usually require an expensive oscilloscope to detect. I highly recommend the Elmo Labs article titled VRM Load Line Visualized to see a great picture of undershoot and overshoot in action. While undershoot and overshoot are temporary spikes, an undershoot that's too low can cause instability. Overclockers and enthusiasts typically use the VR load line to decrease the effective voltage in an all-core heavy workload. Note that in the BIOS we often get a selection of 6 to 8 options for the load line configuration. Still, the voltage regulators offer a much higher degree of configurability, sometimes allowing you to set the load line to the specific milliohm. The presets you find in your motherboard shouldn't be compared to those of other boards and sometimes not even across different BIOS versions. A final tool we have to discuss is the Intel DC load line. Now, to make a long story very short, the CPU PMU, Power Management Unit, relies in some parts on the SVID information to do some power calculations. And if the effective voltage differs too much from the requested voltage, some of those calculations can be a bit off. For example, suppose the voltage frequency point is 1.4 volt, but we've configured the AC load line to 1.45 volt. If we don't tell the CPU that a 1.45 volt VID request results in a 1.4 volt effective core voltage, then the CPU assumes the effective voltage is 1.45 volt. That can skew any power management metrics that rely on this VID information. By adjusting the DC load line to account for the expected difference in voltage between the requested VID and the effective voltage, we ensure the CPU Power Management Unit has the correct information to do its calculations. Typically, the DC load line setting is the last option you adjust to match the CPU VID reading to the effective voltage at the CPU die. So after absorbing all this information, what's next? Well, let's have a look at the default voltage configuration that we used for our stock settings all the way up to OC strategy number 3. The main difference between the motherboard stock configuration and OC strategy number 3 is that we disable a thermal velocity boost voltage optimizations. We do this because we want to undervolt the CPU. By disabling the voltage optimizations, we get a much higher voltage at the top end of the voltage frequency curve, especially in idle, where the CPU temperature is far below the TJ max. That is, despite not touching the voltage for that VF point. In addition, using the negative VF point offset can reduce the voltage used in demanding all-core workloads. For the fourth overclocking strategy, I reset the VF points to their default value of 0 and set the AC load line to 1. Then I check the stability of the OCCT all-core workload. Of course, the system is unstable because the VR load line is set too aggressively. This drops the effective voltage under a heavy workload too much. Adjusting the VR load line too high from standard gives us a more reasonable voltage under an all-core load. It's still not entirely stable with our overclock, so I use the VF points again to increase the voltage for better stability. As a last step, I also adjust the DC load line value so that the CPU VID matches the CPU core voltage. The result is that we have a lower maximum voltage at the top end of the voltage frequency curve and, at the same time, still have a low voltage in our all-core workloads. As you'll see, this configuration yields an extra 60 MHz in our OCCT all-core stress test. The Intel per core ratio limit allows you to set a maximum ratio for each P-core and E-core group individually. That opens up two new avenues for overclocking. First, you can now individually overclock each core and find its maximum stable frequency. 2, you can set a very aggressive turbo ratio overclock while constraining the worst cores. When we set a per core ratio limit, counterintuitively, this doesn't act as a core-specific OC ratio. Rather, it acts as a limit to what parts of the VF curve can be used. Let's say we have a CPU that can run up to 6.4 GHz at 1.6 volt. If we set the ratio limit for a core to 62x, the CPU core will boost up to 6.2 GHz at a voltage interpolated between the 64x at 1.6 volt and the next lower factory fused VF point. In this OC strategy, we use the per core ratio limit function to get 6 of the 8 P cores to 6.2 GHz, whereas the other 2 remain at a maximum of 6.1 GHz. A final topic for this overclocking strategy is the AVX negative ratio offset. Now, the AVX negative ratio offset has been on Intel CPUs since Broadwell E, and what started out as just a negative ratio for the AVX later expanded into an AVX2, AVX 512, and with Sapphire Rapids, even an AMX negative ratio offset. The ratio offset helps achieve maximum performance for SSC AVX and AMX workloads. The specific behavior of the AVX ratio offset has changed over time. Nowadays, the offsets are not triggered immediately when an instruction is detected, but based on the mix of instructions over a certain period. The offsets work according to an elegant frequency license-based approach. The 4 frequency levels are L0 to L3, and each level is associated with a particular load ranging from lightest to heaviest. And then each level is also associated with one specific ratio offset. The most practical example of this impacting our overclock is Cinebench 2024. While it is an AVX accelerated workload, it doesn't trigger the AVX2 ratio offset, causing it to run at the configured all-core ratio. On this system, I found that Cinebench 2024 was the limiting factor for my all-core overclock, since, no matter what, the P-cores of this CPU cannot run Cinebench 2024 at 5.8 GHz. This method of activating ratio offsets makes it slightly more challenging to fine-tune your CPU, since some AVX2 workloads may not trigger the AVX2 ratio offset. I illustrated this in detail in my Alder Lake launch content. There are some additional rules that you need to keep in mind when setting the AVX negative ratio offset. By default, the AVX2 ratio offset is 0. However, the maximum ratio during an AVX workload is the Turbo Boost 2.0 ratio. So effectively, the AVX2 performance is limited to 5.7 GHz when all cores are active and 6 GHz when up to 2 favored cores are active. The AVX ratio offset is applied for each core independently based on the per core ratio limit. Setting an offset of -1, like we do for this OC strategy, results in a maximum AVX frequency of 6.1 GHz for 6 out of the 8 P cores. Upon entering the BIOS, switch to Advanced Mode. In the Tweaker menu, set GIGABYTE Perf Drive to Unleash. Enter the Advanced CPU Settings submenu. Set Voltage Reduction Initiated TVB to Disabled. Set AVX Settings to User Defined. Set AVX Offset to 1. Set AVX Optimum to Enabled. Set Active Turbo Ratios to Manual. Set Turbo Ratio 1 P-core active to 6 P-core active to 62. Set Turbo Ratio 7 P-core active and 8 P-core active to 57. Set Turbo Per Core Limit Control to Manual. Set Turbo P-core 0, 2, 3, 4, 5, and 6 ratio limit to 62. Set Turbo P-core 1 and 7 ratio limit to 61. Leave the Advanced CPU Settings submenu. Set High Bandwidth to Enabled. Set Low Latency to Enabled. Set Extreme Memory Profile XMP to XMP1. Set vCore Voltage Mode to Adaptive vCore. Set VF Offset Mode to Selection. Set VF points 6, 7, and 8 offset to plus 25 mV. Set VF point 9 offset to plus 75 mV. Enter the Advanced Voltage Settings submenu. Enter the CPU VRM Settings submenu. Set CPU vCore load line calibration to High. Enter the Internal VR Control submenu. Set IA VR Config Enable to Enabled. Set IA AC load line to 1. Set IA DC load line to 50. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. We're adding only a bit of P-core frequency to this CPU, so the performance improvements are not expected to be that huge. That said, we get a gain of plus 20.54% in Geekbench 6 Multi and plus 22.71% in AI Benchmark. Not too shabby. When running the OCCT CPU AVX2 stability test, the average CPU P-core effective clock is 5,387 MHz, and the average CPU E-core effective clock is 4,385 MHz with 1.187 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperatures are 26.4 and 30.9 degrees Celsius. The average CPU package power and CPU input power is 364 and 399.6 watts. When running the OCCT CPU SSE stability test, the average CPU P-core effective clock is 5,645 MHz, and the average CPU E-core effective clock is 4,219 MHz with 1.229 volts. The average CPU temperature is 100 degrees Celsius. The ambient and water temperatures are 26.2 and 30.7 degrees Celsius. The average CPU package power and CPU input power are 359.4 and 390.8 watts. Alright, let's wrap this up. It's taken me quite some time to finish this 14900K overclocking guide. Originally, I had planned for this guide to be ready before launch, but leading up to the launch, I spent quite some time away from Taiwan, just traveling, and then when I came back, there were all of these small issues that forced me to continuously postpone the guide. Even though it's a little bit late, I hope you can still find some value from it. Overall, I think the 14900K is quite squeezed already out of the box, which is great for people who just want to plug and play their CPU. For enthusiasts, I think the main tuning opportunity or performance enhancing opportunities are in tuning the memory, undervolting, of course, unlocking the power limits, and maybe also use some OCTVB. I didn't use OCTVB in this guide, but I think by using it properly, I would have probably been able to get an additional 100 or 200 megahertz on top of this 6.2 gigahertz overclock. In the future, I do plan to do more Raptor Lake Refresh guides, so Feel free to stick around if you want to see the 14700K, 14600K, and maybe even some cryo cooling overclocking guides. Anyway, that's it for this video. I want to thank you for watching and the patrons for their support. As per usual, there will be a written version of this video up on my blog. And if you have any questions, you can drop them in the comment section below. See you next time.